Okay, so good afternoon. So now we have a guest from Columbia University. So it's Professor Schuck that is just coming for us, so we should be very happy. He was taking an airplane from New York to Milan. And so Schuck has absolutely a great career. He was studying in Berkeley, and then he got the PhD in Yale, and then he went back, okay, according to Berkeley view, he went back to a minor university, which is Stanford, which is the little university close by.
The junior university.
The junior university of the Bay, Stanford University, working with a guy that is unknown, is Professor Lerner, which just got the Nobel Prize, so few people know it. And then he was a staff scientist at the Molecular Foundry, which is absolutely a great laboratory that is in the Berkeley lab in Berkeley, so he was going back to Berkeley. And then he became the director of the imaging and spectroscopy facility, and after that he became professor at the Columbia University in the mechanical engineering department, working on so many things. And so, since this course is on lasers, I was really thinking that the last work that I was really glad to be also another on upconverting nanoparticles will be fantastic. And so, of course, we can have a presentation of this thing. So thank you, Jim, to be here.
All right, thank you, Francesco. It is great to be here. Thank you for the invitation. Just really great to have the opportunity to do my favorite thing, which is to come and talk about the wonderful work of our students in my group, and to talk science, right? So what I'm going to talk about today, that you can see the title of my talk is amplifying the prospects of upconverting nanoparticles with antennas, new compositions, and ultimately small lasers. And so the organization of my talk today is going to be, I'm going to introduce you to sort of this relatively new luminescent material, these upconverting nanoparticles. I'm going to tell you about sort of our the work we've been doing to try to make them better. I'm going to do most of that, I'm going to describe most of that within the context of using them as luminescent probes, so trying to make better and brighter luminescent probes. And then what I'm going to do in sort of the second half of my talk is then hopefully convince you that these advances we've made end up turning these upconverting nanoparticles into great gain material for making small lasers. And so I'll tell you about our efforts in making lasers, since in the end this is a laser workshop, right? Okay. So on this slide, this slide's about all the things I'm not going to talk about. These are the efforts going on in our group. I'd say our main objective in my group is we want to use light to probe nanoscale, very local environments. So the light acts as reporters, or we make luminescent particles that can act as reporters and tell us about what's going on at these small length scales, and tells us about sort of the different reports on different properties and materials, so we can understand the relationships between different properties and ultimately understand how to engineer materials with new nanoscale properties. So we do a lot of work on looking at so-called quantum materials, 2D materials, and both imaging them and studying their nonlinear optical properties, trying to use them for quantum sensing, etc. But what I'm going to talk most about today is our efforts on this quadrant up here, the upconverting nanoparticles. All right, so here is the outline, which I've sort of described to you already. I'm going to introduce you to the concept of the upconverting nanoparticles. I'm going to tell you what we've been doing to make them brighter and better, and then I'm going to describe how we're using them to make smaller and better lasers. All right, here's a picture of one of our labs, and you can read more about what we do in our group at nanolight.me.columbia.edu. All right, so I usually, as way of motivation, I would just want to remind people that luminescent materials, and especially luminescent particles, are everywhere in the world today, right? They're used for making dye-sensitized solar cells, they're used for making LEDs, displays, and I guess perhaps more importantly, the luminescent particles, luminescent materials, fluorescent dyes, fluorescent proteins, are really the workhorse of most biological studies. And so a lot of people are constantly working and developing new luminescent probes. And so if you're thinking about what would be sort of if you're trying to optimize a luminescent probe, if you're trying to make better ones, you can have a whole list of ideal properties that you want for your luminescent probe, particularly if you're designing it to do some kind of bioimaging, biofunctionality. There really are three main classes of luminescent particles that people are most familiar with. There's organic dyes, right? Dye molecules, organic molecules. There's fluorescent proteins, and there are quantum dots. And so all of these particles, I would say, are really bright. They're really good at emitting photons. But beyond that, they're generally bad. They're generally terrible at almost everything. So they're not photostable. So what does that mean? That means, especially for the organic materials, you can usually get roughly 1 million photons out of them before they die. They photobleach. There's some kind of irreversible chemistry that happens that gets rid of them. People will tell you that quantum dots don't photobleach, and they're lying to you. You can always make quantum dots photobleach, although they are more photostable, absolutely. Another issue is that all of these particles do this so-called blinking. So they turn on and off intermittently, randomly. And so that's not always a problem, but it's a problem, let's say, if you wanted to, say, tag a protein in a cell and track it, watch it move around. If your probe then turns off for a certain amount of time, it's impossible to track, right? So, and it turns out that all of these particles have this blinking problem. The other issue is that all of these luminescent particles, right, are so-called Stokes particles. You excite at one wavelength and they emit at a lower energy. And, well, and that makes sense, according to the conservation of energy, but it's also a problem because it turns out that lots of things, say in biology, also fluoresce. And so this means that the luminescence that comes out of your probe also overlaps with this cellular autofluorescence. And this background is a huge, huge problem for most sort of imaging studies and biological studies. Actually, not just in biology, most imaging studies, autofluorescence is an issue. And then there's a final category I put down here. It's operation in the near infrared. And I'm going to have a slide next that's going to concentrate on why you would want to work more in the near infrared than in the visible. But needless to say, there are really good fundamental physical reasons why you can't design organic molecules to have high quantum yields to be bright in the infrared, and even in the near infrared. And quantum dots are better at working there. However, they're poisonous. All right, so with all that in mind, enter upconverting nanoparticles. So upconverting nanoparticles, it turns out, are excellent at all these other properties. The real question is, can they be bright enough? And so let me begin my true introduction of upconverting nanoparticles by first describing to you why one might be interested in dealing with near-infrared photons. So by way of motivation, I have a plot here. And what this plot is describing is the propagation length of visible photons through heterogeneous material, through tissue. And what you see is that photons only propagate ballistically, which is to say without scattering, for about 100 microns. And after that, they scatter. And so that means all optical imaging that happens right now happens within 100 microns of the surface, right? So that's literally the width of a human hair. And the question is, well, there's a lot of biology and everything else that goes on below that depth, right? So is there a way that you can go deeper? Maybe deeper still. And the way that you do that is to push to longer wavelengths, right? So it turns out that longer wavelengths scatter much less. Turns out that scattering is the main loss. Absorption matters a little bit, but scattering is the main source of loss in these materials. So you want to get to longer wavelengths. The problem, of course, is that I just told you there aren't good luminescent probes in the near infrared. And so you need to find better probes, better local sensors that work in this wavelength range. And so that was some of the motivation for this development of these upconverting materials. Okay, so let me tell you, at least sort of in a simple way, what these upconverters are. So upconverting nanoparticles are essentially ceramic or glass nanoparticles that are doped with lanthanide ions, rare earth ions. And they are very, very efficient at absorbing near-infrared photons and upconverting it so that it emits at visible or higher energy near-infrared wavelengths. To give you some perspective, they are about 5 to 8 orders of magnitude more efficient at upconversion than your best 2 photon dyes. And so that got people excited. And so here's a comparison here for sort of the minimum power needed to get a certain signal-to-noise ratio when you're using upconverters versus quantum dots and organic fluorophores and looking for nonlinear signals. And so what this means is that already with these upconverting nanoparticles, you now can use cheap, $300 Thorlabs diode lasers to do your nonlinear imaging, your multiphoton imaging, rather than a Ti-sapphire laser, right? As a colleague of mine says, Bruce Cohen, he likes to say that they took the $100,000 laser and they put it in the nanoparticle. So that's where it works. And so here's just an example. So, here's a vial of the material. It looks transparent by eye, but if you shine near-infrared light through it, you can see that it emits bright green light. So they work very well, and that's just a CW laser beam. And so why, right? Why do these work so well? And so usually, I put this energy level diagram down in a small part of the slide because I usually breeze over this, but for this audience, I think it makes sense to explain this energy diagram a little bit. So lanthanide ions are sort of unique in that they have these very nice sort of ladder-like sets of excited states in the material. Their excited states, the main issue, well, both the good and the bad of these excited states is that they are optically forbidden transitions. So they don't really like to absorb light very much. But once they do absorb light, these excited states have lifetimes on the order of milliseconds. And so once you get, say, an erbium ion excited to its first excited state, it just hangs out there. And it's relatively easy to absorb another photon and go up to another excited state. You just climb up the ladder for every photon that you absorb. And eventually they recombine and emit a higher energy photon. So that's how these work. And because they have these real metastable excited states, or actually real very stable excited states, it's very efficient at doing this upconversion. So it's sequential upconversion as opposed to multi-photon absorption that happens in dye-molecules. That's why it's so much more efficient. Typically, people will use ytterbium, YB, as a sensitizer, a so-called sensitizer. That's because YB has this one excited energy state, and it has about a 10 times larger absorption cross-section. And so that absorbs your light, and then it funnels it into then the other lanthanides that you use for the emission. And so then you can control, so for example, the color of emission just by changing the lanthanide that couples to the ytterbium. But again, because so it's a double-edged sword. They have very long-lived excited states, but they don't absorb much light. So what we tend to do is you try to pack as many as you can into one particle, at least until other issues start kicking in. So let me tell you about these. All right. Because they're so efficient, though, there are a number of applications that people are starting to pursue using these materials. So they're using them, of course, for trying to improve photovoltaics, for capturing infrared portions of the spectrum. They're trying to make 3D displays. They're trying to use them for security printing and anti-counterfeiting. In fact, I think Australia has money now that actually has upconverting nanoparticles in it. And then, of course, people are using this now to do deep tissue bioimaging. And what we've been pushing on for a while is can they be good sort of single molecule level bioprobes and luminescent probes. So it was now more than a decade ago that we actually first showed that you can, in fact, that these things are bright enough that you can image single particles, single upconverting nanoparticles. And so that's what we're showing here. These are all single upconverting nanoparticles. And perhaps most importantly, what we showed is that they never photobleach. So you shine your light on them and they just keep emitting forever, at least as long as we've left our lasers on them. They also don't blink at all. So they don't bleach, they don't blink. And this got us asking, maybe these are getting close to near ideal single molecule level type bioprobes. The real, question though is, can you get enough signal out of them to do meaningful things? And so, actually, there's a number of questions. The show they had a lot of potential. In order to decide, we wanted to make them better, see if we could make them better and better single molecule probes. There were a number of things you had to improve. You have to make them small enough to be useful. You'd like them to have many colors, so you could multiplex them, for example, the way that people do with dyes in bioimaging. And of course, you want them to be bright. You want them to have a lot of signal, right? It's all about the signal, really. So I'm going to spend the rest of this half talking about our efforts to improve brightness. I've had a number of colleagues who have done a lot of work on improving both the synthesis for making them smaller and for making many colors, and we use those technologies to try to, anyway, in our materials development. Okay, so the way that these particles work is you've got a nanoparticle. Say you start with a big one, say 30 nanometers, and all it is a nanoparticle with emitters stuffed inside of it. And so what happens is as you make the particle smaller, it gets dimmer, because you just literally have fewer emitters inside the particle. And that's, it's one thing if that's the only problem, right? You have this volume scaling, but it actually is worse than that. It turns out that even if you correct for this volumetric scaling, as they get smaller, they get really dim. And the reason for that is, for anyone that's dealt with materials, right, you know that ultimately surfaces start to matter. And at the surfaces of these materials, you get a lot of non-radiative recombination. So surfaces turn out to be bad and give you sort of a dead layer in these materials. And so even though we could make small sub-10 nanometer particles, we couldn't really see them. And so this got us asking, well, how do we make them better, right? The first thing that you think of is, well, can you just put more emitters inside the particle? So as I'll mention in a second, there's sort of a canonical composition, but can you just stuff more material into these particles and try to make them brighter that way? And if you were to ask anyone that developed sort of lanthanide-doped ceramics before, they would say, no, can't do that. And it's because you run into this problem of so-called concentration quenching. But then you ask what concentration quenching means, and things get fuzzy. But what people do know from working with bulk materials is that there is very much a canonical composition. The brightest bulk material, upconverting material, are crystals that are doped with 20% of terbium, right? This is the absorber. And then 2% of your emitter, usually erbium. Erbium turns out to be the brightest. So people here are familiar with erbium lasers, for example. This is sort of the compositions that they tend to use to make them. And so what happens if you put more erbium in there? Two main things come into play. The first is that as you start to increase the erbium concentration, it gets easier for energy to start migrating from one ion to the next, and eventually energy can migrate all the way to the surface, and surfaces are bad, right? So that's one reason. That's one component of concentration quenching. The other thing that goes on is that you get cross-relaxation between the ions. That basically, you again get energy transfer from one ion to the next, but they both end up in lower energy states rather than upconverting to higher energy states. And so again, this sort of effectively reduces your upconverting quantum yield in these materials. This is known to exist in bulk materials. The question is, are these really problems for upconverting nanoparticles? And so we thought that, well, that's a pretty simple question to ask and maybe even to answer, because everyone's been looking at bulk material. Maybe the nanoparticles are different. So we know you have surface losses. We know that if we want to use them as single particle probes, that you need to usually excite them with a little higher power than people typically use for bulk material. Also, we kind of had intuitively this feeling that now in a nanoparticle, you've got this sort of packet of material, and you can, in principle, confine the energy inside this packet. So maybe that's a little different than bulk material as well. And so anyway, there's lots of things that are different. Are there new design rules that come into play? So let's model it. And so here's the excited state energy manifolds for all of your different rare earths. And I put this up here just to remind you that modeling energy transfer between different lanthanides is not trivial. Right? There's some more than 10,000 manifolds that you have to figure out how they all couple to one another. But a guy at the Molecular Foundry named Emery Chan did this and built a beautiful model. And so we immediately asked this question: if we have these other constraints, these nanoparticles, is 20% of terbium, or 22 particles, that's what we call them, 22s. Are the 22s the most optimal? And of course the answer was no, not at all. In fact, what you really wanted was more concentration of emitters in your material. And once you go in and put more emitters in your material, the first thing we did was increase the emitter concentration by 10 times. So we went from 22s to 2020, 20% terbium. And what we saw is that these particles got a lot brighter, as you can see here. So this got us pretty excited. We're now getting kind of 1 to 2 orders of magnitude more signal out of these particles. So that was the first thing that sort of changed. Of course, we did ask the question, well, that's great, but can they be brighter? Can we make them even brighter? The next step to making them brighter is actually something that makes a lot of sense. It's something that really is almost trivial, which is you can put passivating shells on the outsides of your materials, and this helps with this sort of energy migration to the surface. This basically alleviates all of your surface losses. And so what people showed after our paper was that, yes, you can put these inert shells on your material, and once you do that, you can now increase the emitter concentration basically up to the maximum, up to 100% of emitter, or 100% lanthanide, usually maybe 20% of terbium and 80% erbium, for example. Or here they really did go up to 100% erbium. And what they showed is that the main component of this concentration quenching in these materials is actually losses at the surface. When they put the shell on, basically all the supposed concentration quenching went away, which was pretty exciting. So in fact, now we realized we didn't have to listen to the old rules at all, which was nice. And in fact, it turns out it's not even that they just could get bright. It turns out that something somewhat not intuitive became clear, which is that if you actually take your nanoparticles and you design them correctly, and you make a film of nanoparticles, they can be better at upconverting than a bulk crystal. And the reason for that has to do with this so-called energy migration. So here's my cartoon of an upconverting bulk crystal. And so you shine your near-infrared photons onto here, and the near-infrared photons get absorbed, and they transfer their energy to an ion, and then that can just keep transferring energy to its ion. So your energy can migrate away rather than staying in the same ion and then climbing its excited state ladder to get to the upconverting states that you want to get. But if you force the energy to stay in a single particle, well, then it can actually be much more efficient at doing this upconversion. And so this is a concept that is both simple and yet, so for some reason, didn't really occur to most of the field for a while, and including us. So once we kind of caught on, this has really made this field take off. So, so what this means is that if you take upconverters and you put shells on them, now your ideal concentrations, without shells, your ideal concentration was still actually a pretty small erbium fraction, at least for low powers. But now your ideal concentrations, in fact, they're not the ceramic doped with lanthanide. They're basically like 100% lanthanide particles, or well, as we call them, alloyed particles. So they go from being doped to alloyed materials, right? So in this particular graph from one of our papers, what you see is that the best particles were 20% ytterbium and 80% erbium. So there's no more yttrium involved anymore in these structures. And so they're not only, so here's what they look like. You can see there's the core. You do have to put relatively thick shells on them to really prevent the surface losses, usually about 6 nanometers or so. But by doing that, they get very bright. And in fact, so they get bright not only at high pump powers, but they're actually brighter at all powers. Even down at low power, you can see that these compositions are the best. And in fact, what this means is that now we can even image single particles, sub-10 nanometer particles, with 2 orders of magnitude lower pump power than we had seen before. So this is at a density of 350 watts per square centimeter. So what is that? So that's 2 or 3 orders of magnitude better than what we were seeing before. But to give you a little perspective, I think for humans, the FDA allows you to put in a little less than a watt per square centimeter into human skin at 980. So it's approaching biosafe powers for humans, but we're not quite there yet. That said, well, anyway, for animals, apparently they let you put in a lot more. So 350 watts per square centimeter was a big deal for us. We published this paper just last year. Bruce Cohen led this effort. On the exact same day that this paper came out, Steve Chu, one of the laser Nobel Prize winners that we heard about this morning, right, also published a paper where they showed that they could image a single upconverting nanoparticle at 8 watts per square centimeter. And that was in Nature Photonics. So anyway, they quasi-scooped us, I guess. But the real story is actually the particles are the same particles. They just made their particles bigger. So we still feel like ours was better. So that was it. They just made more emitters inside the material. All right, there's my dig. So, but now that we're getting to these low, these are actual, so if you go, by the way, if you're someone here that does single molecule imaging or single particle imaging, you know that fluence is really low. That's even low for doing that can be low for doing single fluorescent protein imaging. And it's way lower than the powers you need to do single particle 2 photon imaging, just for some context. So these results have caught the attention of a number of people, including the neuroscientists. The reason the neuroscientists care is that they've developed these tools, these optogenetic tools. I don't know if any of you are familiar with optogenetics, but the idea behind them is very simple. They've genetically engineered the ion channels in neurons and in other cells so that when you shine light on them, they activate. And so this means you can now activate neurons or silence neurons just by shining light on them. So people have done cool things, scary things like implanted fake memories into mice and things like that. Right? The main issue, though, with optogenetics is that they need visible light to work. And so, as we've already established, visible light does not penetrate very deeply into your brain. And so what they really like about the upconverting nanoparticles is now you can use infrared light, shine them at your material, into your brain, and then put an upconverter, say, right next to your ion channel, and then it can act as an optical relay to take this infrared light, upconvert it to blue or UV light, and then give you this activation. So deep tissue optogenetics is an application that's gained a lot of attention recently. So actually, one of our former postdocs, in fact, showed that you could do optogenetics using upconverters as the visible light source on neurons in a plate. And very recently, a group over in Japan showed that they, in fact, could do deep tissue optogenetics in mice. And the idea is sort of something like this. Anyway, if you can get the upconverters everywhere, then you can maybe control how. Well, the idea is to ultimately learn how the brain works, and then control how it works, I guess, depending on who you are. But I will point out that the main issue, though, even with this study in Japan, is that the powers they had to use to activate the neurons was still extremely high. In fact, they effectively cooked the mouse brain while they were doing it. Bad. So then this leads us to ask the question, can we still make the particles better, right? Can we make them brighter? And so this led us to think about something, a little bit more fundamental within the particles. So even if you have an upconverter, you load it up with as many lanthanides as possible, can the lanthanide, what's the limitation to how bright this particle is? And it turns out that the limitation to the particle is the fundamental limitation is this absorption cross-section of these lanthanides, right? So the absorption cross-section of a lanthanide is really small, 10 to the minus 21 square centimeters. Meanwhile, the absorption cross-section of a fluorescent dye is much larger, 5 orders of magnitude larger, actually, 10 to the minus 16. And so maybe there's a way to combine these two to improve your upconverter. And right, so the solution is to take a dye and use it as an antenna to funnel energy into your upconverter. And so this idea has been, was bouncing around the upconverter community for a while. And while we were all talking about it, Jan Homland's group just did it. Stuck dyes on an upconverting nanoparticle. They published this in Nature Photonics in 2012 and showed that, in fact, they could get 1,000 times brighter particles just by putting dye molecules on it. And so this got a lot of people's attention, right? You just gained 3 orders of magnitude in brightness. This was pretty exciting. And so then all of us groups jumped on this and started trying to study the system, and immediately a number of questions jumped out at us. But maybe the main one that jumped out is, why on earth did this system work? It should not have worked. The dye molecule absorbs and emits about 830 nanometers, and all the absorption in your upconverter is absorbs at 980. There's basically 0 spectral overlap, and so all of your FRET equations told you that there's just no way this energy should be going into your particle. Why did it work? And so anyway, this led people to start looking into that, including us. Some people actually just changed the absorber in the upconverter to neodymium, which does absorb around 900, and they showed that they could get decent enhancement with that, but still not the big enhancement that these folks had got. I'm going to I'll save you all the details, but what essentially we realized is that actually the energy transfer isn't occurring through this so-called singlet level of the dye molecule at all. What's happening is when the dye molecule gets close to the heavy atoms, the lanthanide atoms in the nanoparticle, there's some spin scattering, get a spin flip, and the dye molecules almost instantaneously go to the so-called triplet state, which is at a slightly lower energy. And we were able to figure out where that triplet energy lies, and it turns out it lies almost right on top of the ytterbium absorption. So this was pretty exciting. We now realize the mechanism for how energy gets from a dye molecule into the upconverter. And in fact, it goes through the triplet. So the question became, well, if the triplet is doing all the work, how can we create more triplets? I'll again save you most of the details, but the short answer is you put more lanthanides in your material, more heavy atoms. And the heavy atoms are what induce this intersystem crossing. And so by increasing the lanthanide content from 20% to about 50%, what we saw is that we got 30 times additional brightness just by engineering our particles that way. And so this was so what this means now is we put dyes on our molecule. We changed the composition a little bit so we could really take advantage of this triplet effect, this intersystem crossing. And now we have particles that are 30,000 times brighter than without the dyes. So this got us pretty excited. So yeah, 30,000 times brighter. What actually is more impressive to me than the 30,000 times brighter is the fact that what happened was the upconverting quantum yield improved by 2 orders of magnitudes. So up to almost 10%. So they went from 0.1% to 10% upconverting quantum yield. So this is a nonlinear process with this sort of 10% quantum yield. So now you're starting to approach behavior of like a regular dye molecule, except it's a nonlinear particle, right? That kind of upconverting quantum yield actually matters for a number of other applications as well. So back in 2013, there was a great analysis showing that, essentially asking the question, can upconverters really make solar cells better? And what they said is that, well, as they were made back then, no. What you'd have to do is you had to start getting to essentially upconverting quantum yields on the order of sort of 5 to 10% before you started getting noticeable increases in your solar cell efficiency. And so now we're at the level of where you'd get about 0.2, 0.3% total increase in your solar cell. And while on one hand that sounds small, on the other hand, right, keep in mind that almost every solar cell company now would retool their entire fab line if you told them they could get 0.2% increase in their solar cell. So this actually might be starting to matter. Why else does it matter? Well, first, these are the brightest upconverting materials that exist, period. So that's pretty exciting. So we're trying to figure out what to use them for. I will tell you right now, I don't know if I have it on this slide. I'm talking about all the good things. There is one big downside, which is all the downsides that we have with dyes now matter again for this. So the antennae idea were great, but maybe there are better antennas that aren't so air sensitive. Basically, if you introduce these to oxygen, they photobleach, and that's the downside. For a solar cell, though, that might not actually matter that much because you encapsulate those things anyway and you keep the oxygen. In fact, we showed that when you encapsulate them, these things last for a while. The other thing that matters, the other reason this matters, to understanding how energy goes back and forth between, say, fluorescent molecules or, between molecules and upconverters, is that upconverters themselves aren't great sensors. But dye molecules, the people have engineered all sorts of organic molecules to sense everything from ion concentration to pressure to temperature, et cetera. And so now you can interface those two capabilities and have them work deep in tissue because you're using infrared light to ultimately interface with the molecules. So that's probably another big reason this matters. Yeah, I'll skip past those. And so that's great. But of course, can they be even better, right? Can we get them even brighter? And of course, the answer is yes. The approach then that we thought about taking beyond the dye antenna sensitization was the following. Can we make use of some kind of coherent behavior to make the upconverters even better? And so how do you get emission that's coherent? You make it in layers, right? And so the idea is that as we learned yesterday in the very first talk, incoherent emission essentially has an intensity that scales as the number of emitters. But if you have a coherent emission, it scales as the number of emitters squared. And so this is a big win if we can start taking advantage of this scaling law. And so this now, anyway, bring you back a decade or two. It turns out that actually one of the first reasons that these upconverting materials, these lanthanide-doped glasses and ceramics were even invented was to try to make lasers. So the whole point was that most of the lasers that had been made at first were all worked in the red and the infrared. And what people wanted was other colors too, especially visible colors. And so this was maybe the most efficient way to get those. Nowadays, people have very efficient doubling crystals and things. And I think that's what's in here, right, is a 1064 or something that gets doubled. But that was the main motivation for making these materials. So actually, there's a lot of literature on people making lasers out of these upconverting materials. They're just out of these very large bulk crystals that turn out to be relatively difficult to mechanically manipulate, to fabricate, to etch, right? They're very brittle and they're large. And so that's anyway, that development stalled a little bit. Now, but then you can start rethinking, well, now we've got these sort of the same material, but they're in these perfectly tiny little nanoparticles, right? These little packets of gain material. Maybe there's an advantage here. Now we don't have to just leave them in a crystal shape. We can coat them onto anything. And so people started doing that. This is some great work from a guy named Feng Wang, who's in who's in Singapore, I believe. And so he did start making lasers out of these materials. They're not particularly small, and they're not particularly efficient. He was using the old compositions, the 22 type %. But in fact, you do see that you can take, say, a glass fiber, make a little bulb on it, coat it with upconverting nanoparticles, and you get whispering gallery mode lasers in these materials. And so this led us to think, well, okay, while these lasing thresholds are pretty darn high, 10 to the 10 watts per square centimeter, 10 to the 7 watts per square centimeter, you need pulse lasers to get these to work. Now that we know how to make much, much better upconverting nanoparticles, maybe there's some room maybe there's a little advantage here, right? So we started doing this. Anyway, yeah. So practical applications would benefit from lower thresholds, CW operation in smaller size. Maybe our brighter materials could help with all of these. The last few minutes here, I just wanted to tell you why. So there's a whole area, a whole field of lasers where people are doing nothing but trying to make really, really tiny lasers. And the reason for that is actually very simple, right? If you have really small lasers, that enables completely new technologies that are tailored for operation in very small, very confined, very sort of usually non-laser friendly environments, right? And so you want to make these things small. The main issue is that, anyways, this includes microprocessors, cells, right? There's some beautiful work where people have actually made cells lathes now, right, by putting GFP in them. This is Multigather's work. You want to put little upconverting lasers inside your brain for optogenetics, things like that. The main issue is that as you make lasers smaller, right? We learned about this in our last talk. As you make the laser smaller, you have more and more losses, right? Light doesn't like to be confined into these tiny, tiny volumes, and you get scattering losses and bending losses and everything else. And so what that means is that unfortunately, as you make lasers smaller, you have to pump them harder and harder to get them to lase. And so what I'm showing here is actually a plot comparing, it's smaller cavities sort of in sort of biological scales on the right axis, and laser thresholds on the x-axis. And you can see that most small lasers, especially nonlinear lasers, all have to use pulsed operation to get pumped because they need these high instantaneous intensities to work. And then only for very large lasers can they make CW lasers. All right, so there's this big empty spot down here. Can you make them small and have low threshold that we're trying to fill? And so we did something very basic. We took our very good materials, with Francesco and Luca Moretti here, we put them around something very, very simple, these polystyrene beads. And so these polystyrene beads essentially they're these whispering gallery mode cavities. You just get total internal reflection, again, as we heard in the last talk, that form these nice little optical modes inside the bead. And as they bounce around, first you shine 1064 light in this case inside the material. That goes around and around, optically pumps your upconverter, and then those upconverters, some of the emission goes back into a similar mode, and now you have this gain material in that mode, and they start to lase. And that was the idea anyway. This is what they look like. These are the polystyrene beads. You can even see they're not particularly pretty, but they work well. So polystyrene coated with upconverting nanoparticle. And we did this, and what you saw immediately was these neat, sharp lines. I'm like, oh, this is promising. Okay. And it turns out that, in fact, they do lase. So you start turning up your pump power, and in fact, you do see that they do lase. Here's this stereotypical S-curve showing the lasing and the line narrowing. And so we're pumping at 1064, and we get lasing at 800 nanometers. And we're pumping with CW, they're emitting at CW. So the lasing threshold is about, in this case, 33 kilowatts per square centimeter. But the other cool thing is, these lanthanides emit, they have lots of actually colors that they emit, even a single lanthanide. And so not only does this lase at 800, it also lases in the blue at the same time. So we get simultaneous CW lasing in these materials. The average lasing threshold for all our devices was about 47 kilowatts per square centimeter. And we can, again, control sort of the colors that come out by how hard we pump, for example. So this got us pretty excited. It turns out that they still work if you put them inside of a biological material. So we put them in blood serum, and you can see that, in fact, they still lase. They're also this is sort of an initial demonstration of the sensitivity. Just by changing the local environment, the laser mode shifted around. So that may be good for something. They're also extremely stable. So for as long as we shined our laser on them, they kept lasing. And so if there's anyone here that's familiar with nanoparticle lasers, that that doesn't usually happen. Usually they eventually die. But these just keep going for as long as we'd pump on them. And the temperature increase was only about 0.4 degrees when we're pumping well above the threshold. So they actually don't heat up that much as well, which is also nice. And it gives you sort of a signal that they're maybe somewhat efficient at doing this lasing. And so for the last 2 minutes, 1 minute, 5 minutes, oh, great. I'll use all of it, okay.
Actually, on 6.
No, we get some questions. So, okay, so that's great. That got us pretty excited. These are low thresholds. They're CW. It's the first ever CW room temperature, upconverting laser. And but we want to know, can we make them better? In particular, can you make them smaller? And can you lower the thresholds? And so the way that you do that is maybe by combining them with plasmons. So anyway, this is somewhat related to my plasmon question beforehand. So to give you a little bit of background, there's been a lot of work done. Some have been done in Finland, some by Terry Odom's group at Northwestern, where they showed that you can make these plasmonic nanoparticle arrays. So imagine these particles are made of gold or made of silver. And if you make a large array, what you get is not only just, so every nanoparticle has a plasmon resonance, typically in the sort of green to red region. And that's sort of a broad resonance. But if you make an array such that you can kind of get this coherent scattering off of each particle, you can get a very sharp array resonance mode that has a relatively high quality factor, usually on the order of a few hundred, often up to about 1,000. And so we asked, can we use this mode to get lasing? And so these guys had already shown that, in fact, you can make lasers down converting is the wrong word because that means something, but I don't know, Stokes-shifted lasing, fluorescent lasers, I don't know, what do you call them? But you can get these things to lase, but the problem is that the gain material, the only gain material that could really get to work well in these were these organic dye molecules, and that's bad because they photobleach. They don't last for that long. So immediately we started talking to them, and we're like, well, look, we might have a solid state solution to making your small plasmonic lasers. Oh yeah, there you go. Problem, gain material equals organic dyes equals photobleaching. Right, bad. Okay, so here's what we made. So we took, again, one of these arrays. We put a thin film. Our film was about 100 to 150 nanometers thick of upconverting nanoparticles on top of the array. Here's an SEM of the image. And so the nice thing about these arrays, too, is that it's very easy to couple into the mode. You just design it so that you shine your excitation light normally onto the array, and it pumps the mode. And what you see is that, in fact, it lases, and it lases very nicely. And so, again, in this case, we were using erbium-based particles, so this is lasing in the red at 660. But the thing that really jumped out at us was the lasing threshold. So this is now 70 watts per square centimeter. And we had some that went down to as low as 29 watts per square centimeter. So for reasons that I can't explain right now, we just improved the lasing threshold by 3 orders of magnitude. In fact, you're now getting close to the point where you can just take a big plastic lens and focus sunlight onto your array and make it laze. So a solar-powered upconverting laser, right? And again, so this has us pretty excited. We characterize our beam. It does come out as a beam with about a 0.5 degree divergence in these materials. And again, they're super stable. For as long as we are pumping them, they keep working. We get a little bit of drift. I assume that basically the plasmonic nanoparticles are kind of annealing as we go, but they keep lasing, which is great. And so yeah, no damage even after weeks of periodic operation, which is pretty cool. And so yeah, so this is something that we've submitted now, and but I think it offers maybe a route to easily creating on-chip type lasers that could be useful for maybe communications, maybe biosensing. And to be honest, this kind of reminds me, maybe this is like, early lasers. So I don't know what the right application is. Angel Bravo, the postdoc that's done all this work, we told him to go out into the desert and take some peyote for a weekend and maybe come back with some great ideas of what to do with these things. But really, it's sort of exciting times, sort of in its infancy, we think. So we're trying to figure out the best uses for these materials. All right. Anyway, so I finished with a comparison. So now people have made plasmonic lasers before. People have made upconverting lasers before. No one's made a CW room temperature plasmonic laser before until now. And so that's what we have in our material. And there are, anyway, lasing thresholds that are well below what anyone has seen before. And again, I'll be honest, I can't explain it fully. I can give you lots of hand-wavy reasons for why it should be lower, and then I can give you just as many for why it shouldn't work. So we think there might be other things going on, some kind of super radiance or something else happening here. All right, so anyway, go back to this curve. Now I get to fill it in with our recent technologies, right? So in most curves, up and to the right is better, and this curve low, down and to the left is better. And we're now filling in this space for laser, in terms of a laser sort of parameter space that hadn't been filled before. All right, so to conclude, hopefully I've convinced you that upconverting nanoparticles have a number of advantages over your more traditional luminescent particles and materials, both for imaging applications, but also maybe for lasing and other kinds of technology, photonics applications. We're able to achieve lasing in microlasers, so they're smaller than a red blood cell, and then we're able to achieve plasmonic lasing in particles that are, again, sort of a red blood cell's worth of size in X and Y, but 100 and 150 nanometers thick. So getting smaller and smaller. So these, we'll see what they're good for. All right. Most importantly, let me tell you about the people that have done all of this work. So I just mentioned Angel Bravo, who is now finishing up another postdoc at Lawrence Berkeley National Lab. Shiwei Wu and Gong Han did the original single particle imaging work back in 2009. David Garfield is primarily responsible for doing the dye sensitized work in our lab. Dan Gargas did the original higher concentration material. Chongwan, Kevin Kwok, Emma Zhu, and Kangwan Yao are all current members of our lab who are now starting to apply these materials to other fun, exciting applications. We do all of our upconverter work in a very close collaboration with some of my colleagues at the Molecular Foundry, Emery Chan's group, who I mentioned in the context of the modeling, but who also has synthetic robots for making all sorts of compositions of these materials. It's been really fantastically used. And then Bruce Cohen, who really is a biologist at heart and thinks about the bio applications, but also right? The real difficulty in applying these to biology is you have to functionalize them properly and make them chemically amenable to whatever you're trying to study, and he thinks a lot about that. The Scott-Yellow group, who gave us a lot of sort of the original sort of knowledge and teachings about making lasers, and then made them with us. And then, of course, I already mentioned the Odom group and the Schatz group, who have been working with us on the plasmonic nanolasers. And thank you all for listening.
Okay, yeah.
Jim, a very nice talk. I've never really seen this summary so nicely about these materials. For the last example of the plasmonic laser, I mean, the natural question arises if there's a plasmonic enhancement effect. In particular, maybe the absorption, that there's an absorption enhancement due to plasmonic coupling.
Absolutely. So I think that's part of it. These particular arrays are not tuned to the excitation wavelength, so there is absorption enhancement, but it's not the big resonant enhancement. But what they are tuned to is the emission wavelength. So you absolutely have some Purcell effect going on. And this is all actually within, most of the particles that are contributing here are within like 20 nanometers of the posts, and the rest of the other stuff is just spontaneous emitting noise, essentially. If we could find a way to put the particles. So I think we do have a Purcell effect, but on the other hand, we also have losses, and at the same time, a Purcell effect accelerates the recombination rate, right? And so that, in one sense, what that would do is increase your saturation intensity. And so that could counterbalance some of the effect, So there's some kind of balance going on there. What I think also is happening is it has to do with the very high lanthanide concentrations, because the cross relaxation already allows you to lower the saturation intensity, maybe even more than the Purcell enhancement allows you to raise it. And I think that's maybe where a lot of the advantages are coming. But I also think there might be starting to see room temperature cooperative effects between all these emitters, right? You have millions of emitters now packed within these tiny, zeptoliter volumes that you can imagine maybe are talking to each other or even be driven by other fields that exist inside the system, maybe. I don't know. But I think absolutely, that has to be part of it.
Thanks for the great talk. I have two questions related to the possible applications of these nanoparticles.
Yeah.
One is, well, the first is very simple, it's related to the toxicity, possible toxicity of lanthanides. And the other one is related to the dye triplets sensitization.
Yeah.
I'm not sure if I understood correctly the mechanism, but is there possible having like a triple quenching effect of molecular oxygen while working in in bioenvironments of the triplet states?
And so I think so. It's some kind of like a photodynamic therapy type of application. Is that, I think absolutely that would be a way of sort of making lemonade with the triplet states, yeah, that exist. And in fact, what we learned from that study is that we actually should put even more emitter into our particles. You might have noticed in the quantum yield curve that it saturated and started going down again, and that's just because we were dumping too much energy into the particle, and actually we're exciting up to these UV states that we can't see. But in principle, actually there's a lot of UV light coming out of these systems. We just don't see that in our other people have started to study this. But I think that's actually would be a great use for these types of things. In terms of toxicity, that's a great question. There's a lot of studies that are just now starting to come out on that. And so this is, I'm not going to do, I can't do a very good job of summarizing them, but the main point is that they're way less toxic than quantum dots. That's the ground zero, but okay, what isn't less toxic than lead, right? Or cadmium. But then also, there's been a lot of studies on it, so I told you we'd like to put these shells on the materials to make them, and so it turns out that these shells look like they're pretty darn good at keeping lanthanides from leaching out of the particles. So you put a silicate oxide shell on it, and that helps a lot. So things are looking promising on that. Yeah, it's definitely if you put a core in there, just the core of the material, no shell, you will start to get lanthanides leaching out. So that is you have to be thoughtful about that approach.
Thanks for the very nice talk. So one question about the dye-sensitized nanoparticles. So you say that this intersystem crossing becomes faster when you have close to the heavy metals.
Yeah.
Do you have a time scale for this?
Yeah, about 10 to the 10 per second.
Okay.
Ballpark. Yeah. And we haven't measured it directly, so we're basing that off other people that have coupled their dyes to lanthanide ions. Yeah.
And do you know the quantum yield of the triplet production is pretty high? Then
so we don't. I think in our, and I'd have to go back. So I actually estimated this in the SI. It's high. I think because it just outcompetes everything. Yeah. I mean, even the dye fluorescence is more a couple nanoseconds, right? So it just. But I can't. I don't remember the exact number. But yeah, it's high. That's not the limiting factor in this.
And I have a question regarding maybe super resolution applications of, can you, let's say, switch them like on and off or things like that, or they would just bleach all the time?
So you can't, so with the dye, for the dye sensitized ones, so normally they don't photo bleach. Actually, that's the issue, is that they're always emitting, right? Now that you can dye sensitize, you can put switchable molecules on them. But actually, there may be, it's a good question. It's the heart, so that's the bit, you absolutely, in terms of super resolution, they're so appealing because you can get essentially an infinite number of photons out of them, right? Which means you can do photon localization and know their position to, sub-angstrom accuracy, right? So there are a number, they might be good for approaches like paint, which is where the particle is moving around, but then it'll stick for a little bit of time. And you just image it in that one spot before it pops off into a liquid again and diffuses around and is just sort of in a background. But I think there actually are now ways where you can essentially, depends on what you want to study. So we tend to spend a lot of time thinking about these 2D semiconductors and quantum materials. And actually, they transfer their energy very efficiently into the 2D materials. And so that essentially turns them off. So we can use them actually to probe very local properties of the 2D materials using that kind of approach as they land and then turn off and then turn on and things like that. But I think that is one definite application for why you would want to attach organic molecules or other types of antennas, some kind of functional material on top of them. Now there's some work going on where people are actually, if your host could be a phase change material, then you could potentially turn it on or off or have something else happen. So there are people thinking about that route as well.
Perfect. So I think we thank Jim again, and then we switch to the next speaker.